Understanding the basics of the Emonitor frequency setup. When we're looking at an FFT, we're presented with a variety of peaks at various frequencies. We could click on a peak to set the cursor, and then we can click the Label Frequency button. And Emonitor tells us this is the motor speed. Let's pick another peak, click the button. And Emonitor tells us this is the blade pass frequency. So if we click back on our motor speed, and then we hit the H key to turn on our harmonic cursor, we notice that the cursor for the 3 times harmonic is not the same as the blade pass. There are different frequencies. We could click another random peak, and Emonitor shows us this is the motor inboard ball spin frequency. But how does Emonitor know this? We have to configure the frequency setup view so that Emonitor can make these calculations for us. To find that, we go up to the View menu and select Frequency Setup. When we look at the Frequency Setup view, we see the machine hierarchy pane in the upper left, and then the frequency setup and frequency labels on the bottom part. We can click to various locations, but as you can see, the frequency items don't change. So there's one frequency setup defined for a particular machine. All frequency setups start with the speed reference, which we can define in a variety of ways. It might simply be the number that we type in the speed column, if the machine is a consistent static running speed. But there's a variety of ways that we can define this. Let's take a look at our options. Double-clicking the spectrum RPM, we can define the speed for a variety of sources. In this case, we're going to leave the defined speed for blank so that Emonitor assumes it's the fundamental input speed. And currently, it's configured to use the current spectrum measurement. So the speed that's taken with the spectrum measurement, it'll use that. And then we can point it to the spectrum measurement in the hierarchy that we want it to take that speed from. Alternatively, if we're not getting speed with the spectrum measurement, we can extract it from the current spectrum measurement. And what it does in this case is we provide a target speed range where we expect the speed to be approximately, and a search bandwidth percentage on either side of that peak. Emonitor will pick the highest peak in that band and assume that that is, in fact, the speed that we're looking for. Obviously, this is only appropriate for machines with a fairly narrow running speed. We could point it to a frequency measurement, which is simply a numeric data type measurement that is designed to track running speed. And then we would point it to that specific measurement. We could use, as previously mentioned, the machine speed column, or we could simply define it as a constant speed in the constant speed field. But once we have our speed reference, we can then go on to define our other frequency types. Let's take a look at our options here. In addition to speed reference, we have the constant data type. There's linear to rotational calculation. There's the simple multiply and sum. The harmonics, sidebands, bearing frequencies, belt frequencies, gearbox frequencies, planetary gears. Then we also have motor frequencies and a variety of other motor-related frequency types. Take a look at harmonic to start. We tell it where the fundamental frequency is coming in from, so we know which harmonics we're looking at, in this case motor speed, and we can define how many harmonics we're interested in. Quite simple. Take a look at the belt frequency type. Again, we're adding it from the motor speed as our driver input. We give it the diameters of our driven and driver pulleys and the distance between those pulleys, and Emonitor will automatically calculate the resulting output speed. In this case, we're calling it the fan RPM, and you can call it whatever you want. Now we might want to know what our blade pass frequency is that we saw in our spectrum. In this case, we've got 5 fan blades, so we simply add a multiply frequency type based on the fundamental fan RPM, then we multiply it times 5. That's our blade pass. Let's take a look at bearings. Again, these can be defined from a variety of input speeds. In this case, on the motor side, we'll choose motor speed. And then in the orders box, we can see the variety of fault frequencies related to bearings: ball spin, ball pass, outer race, inner race, cage frequency. And these are all defined as orders of running speed. And this data is usually readily available from the manufacturer's specifications, or quite frequently those bearings may be found in our bearing database by clicking the parts button, and you can see we pick the manufacturer on the top box, and then the resulting model from the bottom box, and recall, and it will populate these for us. We don't have every bearing in the database, but we try to get many of them. They're easy enough to enter in manually if necessary. As you can see, this can be as complex or as simple as needed. That's about it. Thanks for watching.